Yes, good morning. Today we will discuss about the dynamics of a synchronous machine. Before this studying of dynamics of synchronous machine, in the last class we have studied what is power system stability, overview of the power system stability, and the brief history of the system stability, and the different types of the power system stability like rotor angle stability, voltage stability, frequency stability, and under rotor angle stability we have seen different classification, and frequency stability we have seen different classification. So now we will study about the dynamics of a synchronous machine. Usually the swing equation describes the dynamics of a synchronous machine. So to derive the swing equation we require inertia constant. So basically what is this inertia constant? So inertia constant and the angular momentum play an important role in determining the transient stability of the machine. Usually the transient stability means it's a large disturbance which will occur in the road, which will come under the rotor angle stability. Now the per unit inertia constant H in megajoules per MVA, this I will explain in further derivation, which is defined as the kinetic energy stored in rotating parts of the machine at synchronous speed per MVA rating of the machine. Here we are taking synchronous speed, the mechanical synchronous speed. Now rotor kinetic energy at synchronous rotor kinetic energy at synchronous speed is given by K equals to of J omega S, means it is synchronous mechanical, into 10 raised to minus 6, because I will express this in megajoules. So because of that I use here 10 raised to minus 6. Then this, how this equation had been derived, you can go to that Kimbark book, that is very book. For your purpose it is not required, just kinetic energy stored is of J into omega s is my mechanical synchronous speed, into 10 raised to minus 6 megajoules. Now what is J? J is moment of J is moment of inertia of rotor. In some books he had, instead of J they had been given I. No issue. J is moment of inertia of rotor. It is kg square meter. So omega s it is synchronous speed in mechanical. So which is given in radian per second. So how to convert this into electrical? We have studied about the basic equation theta E equals to P by theta M. That means theta electrical can be found out by P by 2 into theta M, where theta M is mechanical degree, theta is electrical degree, P is number of poles. In similar way, here also instead of theta they had been, we will say omega S. So omega S electrical equals to P by 2 omega S mechanical. This is my equation number 2. So this is rotor speed in electrical radian per second. Now where P, as I said, P is number of poles of a machine. Now from equation 1, from this equation and from this equation, equation 2, from this equation, so we can get, from equation 1 and 2 we can get, so instead of omega s mechanical I will use this equation I want in electrical. So Ke equals to of J 2 by P omega s electrical. What we did here, yes. So this we have substituted in terms of, so if this gone, if my denominator goes to here, it becomes numerator and 2 by P. So WSM equals to WS electrical into 2 by P. So the same thing here we got. So into WS electrical. So now I will take the whole term this as an, this term I will take it is an J. This term I will take as a J. So sorry, I will take it as a M, not J. I will take it as an M. What is M? I will explain. Now Ke equals to half M omega S electrical. Let us say this is equation number 3. Now, so M is my J into 2 by P square Ws electrical into 10 raised to minus 6, this equation. So what is M here? Moment of inertia in megajoules per electrical radian. How that megajoules I will explain you. Now we shall define the inertia constant H such that GH equals to Ke of M omega S electrical megajoules, right? Now inertia constant. Now, so what is GH? What is G? It is a three-phase MVA rating of the machine. That means it is a base MVA rating of the machine. H is inertia constant in megajoules per MVA or megawatt second per MVA or second. So how it is megajoules per MVA or megawatt per second, that I will explain. Now let us see here, my omega equals to joules per sorry, watt, it's not omega, watt equals to joule per second. Now J equals to omega second. Now if I want in larger quantity, it is megajoules equals to megawatt second. Now if you divide megawatt by MVA, then you will get M megawatt by MVA, it is a dimensionless, so it will be 1, so it remains second only. So the same he had been given here. So megajoules per second, so electrical radian. So M equals to, so with this equation, yes, now you can see from this equation M I will get, if 2 gets here, 2GH by omega S electrical. So the same thing from equation 5 we can write that M equals to 2GH omega S electrical. So 2GH by 2 pi F. This is omega S is in electrical, 2 pi EF. I required in electrical form. So 2 and this 2 get cancelled. Now what will get? M equals to GH by pi F. This is megajoules per second electrical. Sorry, megajoules second per electrical radian. So here we have derived that. Now if I want to in degree, so instead of pi you make it as in pi equals to 180. So you will get M equals to GH 180 F megajoules second per electrical degree. Let us say this is equation number 7, this is equation number 6. Now M is also called inertia constant, whereas like H, M is also called as inertia constant. Now assuming G as base, the inertia constant in per unit is given. Assuming G as base, that means my base power. What is my per unit power? Actual power by base power. So G as my base power. So M equals to, that's what I written, M equals to GH by pi F. So divide M by both sides. It's not divide M by both sides, it is divide by G by both sides. So it is base MVA. Basically it is a three-phase base MVA. Divide G by both sides. So m by j, m is my actual and g is my base. So you can write as m by g is my m per unit. So G is my base and M is my actual. So I can write M per unit. So here H by pi F. So G and G will get cancelled. So H by pi F. So second square per electrical, this unit is written as second square per electrical radian. How this second square per electrical radian? We'll see. Yes. So when we divide by G, G is nothing but three phase MVA rating as I said. So here what is my MW? It is nothing but here 1 minute. Clearly I will explain. Yes. See here MJ is nothing but MW second. So this we have where this MJ second is equals to MW second, where we will got from here. MJ equals to this, from this we will get MW second. Now Mj equals to m second. Now put this equation, put this in this form, you will get Mw by Mva into second square. So here, so where is Mva? Mva is nothing but by G. It is in three phase base Mva. So now MVA, already it is MJ second square. Now I place this MW second. Now MW second square per electrical radian. Now when we divide by G, so G is nothing but my base MVA. So MW by MVA, it is a dimensionless quantity. So only you will get second square electrical per radian. MPU, M per unit will be given H by pi of, so second square per electrical radian. So this, how we got this second square per electrical radian? Usually we have M equals to GH by pi of. So when we divide by G on both sides, so this is m by G, will get MPU and H by pi of, what is G means it is my base MVA. So MJ per second is how derived here, it is nothing but MW second, this MW second. So now I place MW second electrical radian. Now this equation I place here MJ second. Yes, I place here mj second. Now we will get it is mw second square per electrical degree, electrical radian. If I place here, if I place here, it becomes degree. If I place here, it becomes radian. No. So MPU equals to h by 180f second square per electrical degree. That is your equation number 9. Now coming to the swing equation. So basically the swing equation describes your the dynamics of synchronous machine. Now let us consider generator and motor. So this is very important. Let us give the example for generator. Let us derive for the generator, synchronous generator. Now see, this is my mechanical input power and this is my generator and this is my electrical. You see the direction is here that my mechanical torque and my direction of the shaft, rotation of the shaft will be in the same direction. So that means my Tm drives my shaft in the direction of rotation of generator, that is in the direction of shaft rotation, where this Tm gets through the prime mover. So prime mover is generally an or turbine, either it may be in a idle, small idle, or it may be a steam. So basically what I mean to say is my mechanical torque or input mechanical torque drives the shaft torque in the direction of the rotation of the generator. Now this at the same time my opposing this is torque. Due to this mechanical torque, an electromagnetic torque will set. So this electromagnetic torque or electrical torque will set in opposite direction. So that's is when you go to the motor, it is opposite. So here my mechanical torque drives the shaft torque. Due to this, in reaction, my electrical torque will be developed in the opposite direction. That means my Tm is my driving force and my Te is opposing force or controlling force. Now, the same he had been given. Consider a synchronous generator, develop an electromagnetic torque and corresponding electromagnetic power while operating at synchronous speed. We will considering here the generator is rotating at synchronous speed, assuming that all losses are negligible, winding, friction and iron loss torque is negligible. So all the losses we are considered, it is negligible. Now if the input torque provided by the prime mover at the generator shaft, then under steady state condition without any disturbance, T equals to Tm. That means when losses are neglected, I will consider my driving force is equal to the opposing force or controlling force. In the sense, my generator, my shaft rotating at constant speed. Don't think that both are driving force and opposing force are equal means the shaft will not be rest. In the sense, the shaft is rotating at constant speed. Now let us assume that if my input power is more, if my mechanical torque is more, then my then when you compare with the electrical torque, my mechanical torque will be more. Means if Tm is greater than my Te means then your alpha, that is difference in that, will be of positive. When it will be positive? When my input power will be greater than the my opposing force. That means my driving force should be greater than my opposing force. At that time my alpha will be positive. If my opposing force will be greater than driving force, then my alpha will be negative. So usually this, if positive means the shaft accelerates, and if it is negative means the shaft deaccelerates. So when my mechanical torque will be greater than the when my driving force will be greater than the opposing force, then my generator speed increases, shaft speed increases, that is accelerating. When my electrical torque or electromagnetic torque is greater than the mechanical torque, that means when my opposing force or controlling force is greater than the driving force, then your shaft going to decelerate. So the same here had been given. Under steady state condition without any disturbance, Te equals to Tm. That means my generator is rotating at constant speed. Shaft is rotating at constant speed. Now, therefore, we have Te into Ws multiply omega in both the sides. So Te into omega s and Tm equals to omega s. Tm into Te omega s equals to Tm omega s. That means output power equals to input. To what is P? It is torque into omega. Then, so you can see Tm omega s minus Te omega s equals to mechanical power minus electrical power equals to 0. Let's consider this is an equation 12. If there is a departure from steady state occurs, either your shaft going to your generator shaft going to accelerate or generator shaft going to deaccelerate. When it is going to accelerate, when your when your driving force will be greater than your opposing force. At that time it accelerates. When it deaccelerates, when your driving force will be lesser than the opposing force or controlling force. Here, for example, a change in load or a fault, the input power is not equal to the my output power. That means whenever there is a change in load or a fault, the input power is not equal to the my electrical power. That means my mechanical power is not equal to the electrical power. Therefore, the left side of the equation 12, this equation will not be 0. So, this varies and an accelerating torque comes into the play. So, when accelerating torque comes into the play, when my input power is more, when my driving force is more than my when driving force is more than controlling force or opposing force. If Pa is the corresponding accelerating or deaccelerating power, then so this had been given Pa. So Pm minus Pe means it is an accelerating force. So he had been given that m equal Pm minus Pe equals to m into d square theta e dt square by dt square plus d theta e by dt, which is equals to the my Pa, accelerating power. So this m is defined in equation 8 and 9. Now where is equation 8 and 9? Yes, m is derived in equation 8 and 9. You can see mpu equals to h by pi f, and if you want in degree it is mpu equals to h by 180 pf. This is my equation 9. Now yes, d is damping coefficient, theta is electrical angular position of the rotor. This I will explain. See here theta e and here let us say reference rotor axis and this is theta. Consider only these two. Now consider only these two. Now consider that only the two. Yes, consider this and this. What will happen if reference rotor axis kept stationary, if I kept this stationary, and this my rotor is always my rotor field is always rotating like 360 degree. This is reference, it comes one cycle, two cycle, three cycle, like that. We don't know whether it is rotating at the synchronous speed or not. So the problem can be solved by taking, what I will do is I will move this reference rotor axis along with this. Now take this one more equation, like do here no space, so here space is there. Take this like this. This is my stationary. Now yes, initially this is my stationary, this is my reference axis and this is my This is my theta. Now this is my rotor field. Rotor field. Now if I make R as a constant, so this will continuously rotating. So this is continuously rotating 360-degree. So when it comes to here, one cycle and again it continuously rotating. Now we cannot judge exact where the synchronous speed. So what we will do is, instead of that, keeping reference as a stationary, we'll move both simultaneously. So here R and this is rotor field. Instead of theta, what I will do, take it is an angle like this. Wait. Now see this. Yes. Now what I will do? Yes. Now let's see, it's a delta. Now what I will do is, my both the phasors will move. If there is, it is rotating in synchronous speed, if both will be rotating at synchronous speed, my delta will be constant. If there is a change in the synchronous speed, if there is any change, if the either it will be increase or decrease in synchronous speed, my delta will going to change. Either delta will increase or delta will decrease. So my, if it is delta, if it is constant, my generator is running at synchronous speed. The same thing here had been given. When you delta equals to theta E, the entire this, minus my WS, reference rotating axis, that is in mechanical, remember that, into T. Now when we double differentiate with the above equation, you will get d square delta by dt square, d square theta E by dt square. Now, so finally you will get d square delta by dt square equals to d square theta E dt square. Just interchange. This is my equation 15. Now, where this is delta E is the power angle of the synchronous machine, or it is also called as torque angle. In some books they will be given it is an torque angle. So my delta is the power angle of the synchronous machine. If it is constant, then it is rotating at synchronous, generator is rotating at synchronous speed. Neglecting damping torque, that is D equals to 0, we will not consider damping torque, and substitute equation 15, this equation 15 in equation 13. Now where is the equation 13? So this is equation 30, and consider this is in 0. So if it is a 0, the entire term goes to 0 here. Now, so Pm minus, yes, you will get m d square by delta, d square delta by dt square equals to Pm minus P. Now, using equation 16 and 6, where is 6 equation? Yes. Yeah, this is equation 6. So, it had been given m equals to gh by pi of electrical, that is megajoule second per electrical radian, using 16th equation. Yes, 16th equation this is. Now, using both the equation we will get, instead of placing m, here we will be place gh by pi of, in m place we will use, in m place we will use gh by pi of d square delta by dt square equals to Pm minus Pe megawatt, dividing throughout by G with the MVA rating of the machine. So what you will get, dividing throughout G the MVA rating of the machine. So here if I divide with by J, you will get MPU. So d square by delta dt square, Pi, this is Pm. In some books they had been given, it is input power. So in Nagrath and Kotari they had been taken only PEM. So PEM minus PU. So when this is my actual power, this is my actual power. If I divide by G, that means G is my base 3-phase MVA rating. Now it will become PU here also. Now what is MPU means? My H by pi of. MPU is nothing but my H by pi of. So MPU is H by pi of. This is equation number 19. Now, or this can be written as H by pi of d square by delta equals to Pm minus P. So, H by P of d square delta by dt square Pm minus P, this is my swing equation. So, this it describes the swing equation describes the rotor dynamics for a synchronous machine. It is also used for in analysis of transient stability and for the second order equation. So thank you. In next class, based on this, we will solve simple problems. So please free to ask the doubts. Thank you once again.